Welcome to the Developing DDR and LPDDR Solutions with FPGAs training. My name is Dunia Abdulrazak, and I will be leading you through today's session. Before we get started, I'd like to introduce myself. As I mentioned, my name is Dunia Abdulrazak, and I'm an applications engineer here at Lattice Semiconductor. I have over 7 years of experience in the semiconductor industry and focus mainly on driving customer improvements regarding LPDDR and DDR solutions. Prior to joining Lattice, I held positions as an applications engineer and an IP designer regarding DDR and PCIe. I also attended Worcester Polytechnic Institute, where I earned my master's and bachelor's degree in electrical and computer engineering. Now that you know a little bit about myself, let's dive into today's agenda. In today's training session, we'll first go over the different types of DDR and LPDDR SDRAMs. After that, we'll cover Lattice DDR and LPDDR solution offerings, followed by a walkthrough of the design flow, and then we'll wrap up with an overview of useful information available to you, and then open up for Q&A. Let's kick things off with an overview of DDR and LPDDR memory devices. SDRAM, which stands for Synchronous Dynamic Random Access Memory, was first introduced in 1992 and clocked 1 word of data per clock cycle, typically on the rising edge. In 1998, Double Data Rate, or DDR SDRAM, was introduced. This allowed data to be clocked on both the rising and falling edges of the clock. 10 years later, the first low-power version of DDR SDRAM was introduced in 2008. So what's the difference exactly between DDR and LPDDR memories? Well, DDR is typically used in applications where high performance is an absolute requirement, and LPDDR is a more power-conscious solution intended for applications with low power requirements. Taking a look at this table, you can see that DDR typically supports wider channel widths and higher densities compared to LPDDR. This makes the DDR technology optimal for high-performance applications such as servers, cloud computing, and more. LPDDR, on the other hand, has a narrower channel width but offers several power-saving features, which makes it ideal for mobile and automobile applications. In this training, we'll focus on the memory technologies highlighted in blue, which are DDR3, DDR4, DDR5, and LPDDR2 and LPDDR4. Now that you have an idea of the differences between DDR and LPDDR, let's dive into some of the details regarding these technologies. On this slide, we'll compare DDR3 to its previous generation of DDR2. DDR3 introduced new features such as flyby topology, dynamic on-die termination, and write leveling to enhance performance and signal integrity. In the figure shown here, you can see a depiction of what flyby topology refers to in terms of layout and routing. The memory controller has a direct line to each of the data lines for each memory module, shown in blue, and the command address and clock signals are in a daisy chain, shown in yellow. This reduces the amount of simultaneous switching noise in the system by skewing the data toggling for each module. You might be asking yourself, if this topology introduces skew, then how do we ensure that when we are writing or reading that the timing is okay between the clock, data strobe, and the data signals? The answer is write and read leveling, which are calibration stages introduced in DDR3 and DDR3L to compensate for the skew in flyby topology. Shifting our focus now, let's talk a little bit about dynamic on-die termination, or ODT. Dynamic on-die termination allows each memory module to switch between high or low termination impedance without having to issue a mode register set or MRS command. This improves bus scheduling by reducing bus idle time and improves signal integrity within the system by reducing the amount of signal reflections when writing to memory. As you can see in the figure, comparing the eye diagrams with and without this feature, the diagram on the right, where ODT is enabled, produces a cleaner I, translating to more marginality within the system. Comparing DDR3L, which stands for DDR3 low voltage, to traditional DDR3, it offers the same benefits with an added advantage. It consumes less power and generates less heat since its operating voltage is 1.35 volts compared to DDR3's 1.5. Moving on, we'll now briefly discuss the new features introduced in DDR4 that allow a faster and more power-efficient memory solution compared to DDR3 and DDR3L. DDR4 introduced command and address parity to help with error detection during memory writes and reads. Data bus inversion, or DBI, counts the number of ones on the data line, and if the count is 5 or more, the data bits are inverted. This helps to improve power efficiency and signal integrity within the system, as shown in the figure, where the bottom image represents when DBI is enabled and produces a bigger I. Internal VREF, which was also introduced in DDR4, alongside VREF training, help to reduce data error rates by maximizing data margins. Next, we'll take a look at DDR5, which contains improved bandwidth and enhanced system management features compared to DDR4. DDR5 adopts a dual-channel architecture, compared to the single-channel architecture used in previous DDR generations. As you can see in the figure, with a dual-channel architecture, the data path is shorter compared to single-channel. This results in lower latencies and increased efficiency during data accesses. DDR5 also introduces on-die ECC to ensure data integrity and command address inversion to improve reliability. DDR5 also supports internal VREF not only for data signals, but also command, address, and control signals. The DDR5 protocol also contains integrated enhanced system and thermal management. This is achieved by leveraging a serial presence detect, or SPD hub, that enables communication over I3C for system configuration and thermal management via power management integrated circuits. Switching gears, we'll now take a look at LPDDR2 and LPDDR4. Comparing LPDDR2 to its previous generation of LPDDR, it contains a faster data rate and reduced pin count. LPDDR implemented a 19-bit single data rate command and address bus, whereas LPDDR2 contains a 10-bit double data rate command address bus that is multiplexed. As you can see in the figure, a read operation for LPDDR2 takes 2 clock cycles, where the activate command takes 1 and the read command takes another. Looking at LPDDR4 now, it has better performance and power savings compared to LPDDR2 and LPDDR3. With LPDDR4, it further reduced its pin count by adopting multi-cycle commands on a 6-bit SDR command and address bus. As you can see in the figure, a LPDDR4 read operation takes a total of 4 clock cycles, where the activate command takes 2 and the read command takes another 2. At first glance, it may seem that LPDDR4 takes longer to execute commands compared to LPDDR2. But due to the higher clock frequency and longer burst lengths supported in LPDDR4, control signals can be highly multiplexed without the command and address bus becoming a bottleneck. LPDDR4 also supports on-die termination, internal VREF for data and command and address signals, and command bus training and VREF training, all to improve signal integrity and data integrity within the interface. Now that we've covered some of the features introduced with each of these DDR and LPDDR protocols, let's quickly compare some of the more technical specifications. Looking at DDR3, DDR4, and DDR5, you can see that the maximum clock rate and data rate increase with each generation, going from 1066 MHz for DDR3 to 1600 MHz for DDR4 and 3200 MHz for DDR5. In regards to LPDDR2 and LPDDR4, you can see that for LPDDR2, it has a maximum clock rate of 533 MHz, and LPDDR4 has a max clock rate of 1600 MHz. Comparing the channel widths, DDR3, DDR3L, and DDR4 are single-channel interfaces supporting up to 64-bit wide data interfaces, whereas DDR5 supports 2 channels, where each channel is a 32-bit wide data interface. Comparing LPDDR2 and LPDDR4, you can see that LPDDR2 supports a single-channel 32-bit interface, and LPDDR4 supports 2 channels, where each channel is 16 bits wide. In terms of prefetch and burst length, you can see that DDR3 and DDR4 contain an 8N prefetch with burst lengths of either 8 or 4. With DDR5, the prefetch and burst length are doubled. With LPDDR2, the prefetch is 4N and the supported burst lengths are 16, 8, and 4. With LPDDR4, the prefetch is 16N and the supported burst lengths are 32 and 16. Comparing operating voltage and I/O standards, you can see that the DDR3 and DDR3L operate at 1.5 volts and 1.35 volts using stub series termination logic. DDR4 and DDR5 operate with DDR4 and DDR5, the operating voltage is reduced to 1.2 volts and 1.1 volts, where both memory protocols use pseudo open drain termination. Looking at LPDDR2, you can see that it operates at 1.2 volts and uses high-speed unterminated logic, compared to LPDDR4, which operates at 1.1 volts and uses Looking at LPDDR2, you can see that it operates at 1.2 volts and uses high-speed unterminated logic, compared to LPDDR4, which operates at 1.1 volts and uses low-voltage swing termination. To summarize, DDR and LPDDR technologies continue to advance with each generation, resulting in higher bandwidths and lower power consumption, where DDR memories tend to excel in terms of performance, and LPDDR memories excel in the realm of low power. Now that we've covered DDR and LPDDR memory devices, let's take a look at specific solutions offered by Lattice Semiconductor. In regards to this training, we'll focus on the devices listed here. For the Nexus platform, we'll discuss Crosslink NX, Certus NX, and Certus Pro NX and Mach X05 NX. For the Avant platform, we'll discuss Avant E, Avant G, and Avant X. Taking a look at these products, you can see that DDR3 and DDR3L are supported for all devices apart from Avant E. DDR3 solutions are currently available for the Nexus platform with a maximum data width of 32 bits and a maximum data rate of 1066 megabits per second. Avant G and Avant X devices will support DDR3 in the future with a maximum data width of 72 bits and a maximum data rate of 1866 megabits per second. As you can see in the table, DDR4 is only supported in the Avant platform. DDR4 support will be enabled in the near future with a maximum data rate of 1866 megabits per second for Avant E and a maximum data rate of 2400 megabits per second for Avant G and X, both having a maximum data width of 72 bits. In regards to DDR5, only Avant X devices will contain DDR5 support, with a maximum data width of 72 bits and a maximum data rate of 2133 megabits per second. Switching gears to discuss LPDDR protocols, as you can see in the table, LPDDR2 support is currently available and only supported in the Nexus platform, apart from the Mach X05 NX device. In Crosslink NX and Certus NX, the maximum data width and data rate are 16 bits and 800 megabits per second. In Certus Pro NX, the maximum data width increases to 32 bits. Looking at LPDDR4, it is supported in all devices apart from the Crosslink NX and Certus NX. Currently, the LPDDR4 solution is available for Certus Pro NX and Mach X05 NX, with a maximum data width of 64 bits and a maximum data rate of 1066 megabits per second. An LPDDR4 solution is also currently available for the Avant platform, with a maximum data width of 64 bits. Avant E will support a maximum data rate of 1866 megabits per second, and Avant G and X will support a maximum data rate of 2400 megabits per second in the future. In terms of how each of these solutions are packaged, you can see that for the Nexus platform, it consists of a soft controller and PHY implementation, whereas the Avant platform contains a hardened controller and PHY. Additionally, the Nexus platform supports the native interface, where AXI4 is only supported in the LPDDR4 solution. For the Avant platform, only the AXI4 interface is supported. Looking at the available solutions in a little more detail, you can see that each of these protocols are supported in the component format, with only DDR4 and DDR5 supporting DIMM. Additionally, the by8 memory configuration is supported for the DDR protocols, and the by16 is supported in the LPDDR protocols along with DDR3 and DDR3L. Currently, each of these protocols supports single rank configurations, where dual rank will be added in the future for DDR4 and LPDDR4. Data bus inversion is supported in DDR4, DDR5, and LPDDR4, where on-the-fly burst links are supported only for DDR3, DDR3L, and DDR5. All other protocols support fixed burst links, including DDR3 and DDR3L, which supports both on-the-fly and fixed. In terms of the reference clock for each of these memory controllers, it is configurable for all solutions apart from the LPDDR4 solution targeting Nexus devices. For the Nexus platform, the LPDDR4 solution has a fixed reference clock of 100 MHz. Finally, in terms of the DDR to FPGA clock ratio, 4:1 is supported only for DDR3, DDR3L, and LPDDR2. All other protocols support the 8:1 clock ratio, including DDR3 and DDR3L, which support both 4:1 and 8:1 ratios. Now that you're familiar with the features supported in each of these memory solutions, let's quickly go over the design flow. To start out, you'll have to create a Radiant project. This can be done by selecting File, New, Project after launching the Lattice Radiant software. After clicking Next, you'll be prompted with the New Project window. Here, you will specify a name and a save location for your project. After pressing Next twice, you'll then be able to specify the device family, package, operating condition, and performance speed grade of your target device. Next, you'll then be able to specify the desired synthesis tool. At this point, you would have completed creating your Radiant project. Now, to configure and generate one of the memory controller solutions we have covered previously, you would select Tools and IP Catalog. This will open the following panel within Radiant, where under IP, Processors, Controllers, and Peripherals, you will be able to see all of the memory controller solutions you have installed. If none are present, you can download them from the IP on Server tab. Once you see the desired memory controller solution, you will double-click on it to open up the Module IP Block Wizard window. Here, you will enter a name for your IP instance and then click Next. At this point, you will now be able to configure your memory controller IP settings. On the first tab, you can specify things like the desired I/O buffer, target frequency, and data width, and enable features such as DBI, ECC, and dual rank if they are available. On the Memory Device Timing tab, you will be able to change the protocol timing parameters based off of your selected memory component's datasheet. And then the final Training tab will allow you to tweak parameters tied to the DDR or LPDDR calibration process. For more information on how to configure these parameters, you can refer to the IP user guide for the target memory controller. Once you have configured your settings, you can then click the Generate button. This will open the Check Generated Result dialog box, which will look like this. Once you click Finish, the memory controller will be added to your Radiant project. Now that we have covered how you create a Radiant project and how to configure, generate, and add a memory controller instance to your project, we'll now transition to talking about how we run the provided example design. To do this, you'll have to add the top-level file called eval-top. You can do this by selecting File, Add, Existing File, and navigating to the eval folder within your project directory. After you add the top-level eval-top file, you will then need to add the pre- and post-synthesis constraint files. These are also located under the eval folder. Keep in mind, however, that these files will be overwritten if you regenerate your IP, so it is recommended to check the option to copy the file to your directory when adding these to your project. After adding your constraints, you can then open up the post-synthesis constraint file to specify your pinouts. Once you've completed adding your pinouts, you are then ready to run through the synthesis flow to generate the bitstream for hardware testing. After you are able to successfully program your device, you can then run through the example design, which leverages a UART interface and will provide you with the prompt shown here on the bottom left. For more information on how to constrain, add pinouts, and evaluate the example design on hardware, you can refer to the IP user guide for the target memory controller. On a similar note, you can also simulate the provided example design. In order to do this, you will have to add the eval-top file covered previously, as well as the tb-top file. This file can be found under the test bench directory in your project directory. After adding this file to your project, you can then launch the simulation wizard to generate and launch your simulation environment. For more information on what changes are necessary and how to go through the simulation generation process, you can refer to the IP user guide for your target memory controller. At this point in the training, you should be familiar with the different DDR and LPDDR protocols available, the specific solutions offered by Lattice Semiconductor, and have an idea of how to generate and configure a memory controller instance. In this section, I'll briefly discuss the resources available to you to help you throughout your design process before opening up for Q&A. In terms of documentation, there are two main sources you can refer to. The first is the IP user guide that I've mentioned briefly throughout this presentation. This document covers information regarding the memory controller IP and includes information such as supported features, IP architecture, necessary clocking and reset handling, configuration and generation of the IP, as well as useful debug information and tips and tricks. The other type of document is the High-Speed I/O User Guide. This document covers information regarding the device families and includes information such as the I/O bank and DQS lane structures, clock trees, guidelines for pin and board design, as well as I/O primitive descriptions. In terms of resources available to you to help you get started with your memory solution, we have several boards, reference designs, and demos. As you can see, for Crosslink-NX, we have the PCIe bridge board available, which supports up to a 16-bit DDR3 interface. For Certus-NX, we have the Versa evaluation board available with DDR3L demo showcasing 16-bit support with fixed and on-the-fly burst transactions. For Certus Pro-NX, we have two boards available, showcasing 32-bit support, the Versa board and the PCIe bridge board. There is also a RISC-V to LPDDR4 reference design available for the Versa board, showcasing free RTOS booting from LPDDR4 memory. For Mach X05T and X, we have the development board with 16-bit LPDDR4 memory on board. Switching over to the Avant platform, currently we have the Avant E evaluation board available with 16-bit support. A 32-bit version of this board will be released in the near future, as well as a RISC-V to LPDDR4 reference design. Similarly, for Avant G and X, we will have the Versa board available with 32-bit LPDDR4 memory on board with a reference design. Currently, for the Nexus platform, we have three memory controller solutions available: DDR3 and DDR3L, LPDDR2, and LPDDR4, with a DDR3L demo available for Certus-NX Versa board and a RISC-V LPDDR4 reference design available for Certus Pro-NX Versa board. For the Avant platform, we have the LPDDR4 memory controller up to 64-bit support at 1200 MHz. In terms of solutions coming soon, we have three new memory controller solutions in the pipeline: DDR3L, DDR4, and DDR5, and the release of a RISC-V LPDDR4 reference design for the Avant E eval board and Avant G and X Versa boards. That concludes the content of this training. We'll now open up for Q&A, where you can enter your questions via the chat box. I see a question here asking, I noticed in the presentation LPDDR3 was not covered. Does Lattice have an LPDDR3 solution? Good question. So we do have an LPDDR3 solution, but it is available on our previous generation of devices, such as ECP5. For the Nexus and Avant platforms, we currently do not have an LPDDR3 solution, mainly because we didn't see a market demand for this request. I see another question here asking, does Lattice support LPDDR4X in addition to LPDDR4? So for everyone's knowledge, the main difference between LPDDR4X and LPDDR4 is that it offers additional power savings since its operating voltage is 0.6 volts compared to 1.1. To answer your question, LPDDR4X is not currently supported in any of our Nexus or Avant devices, but it might be something to look into for the future. Okay, another question here. On one of the slides covering Avant, you mentioned DDR4 support is up to 2400 megabits per second, but DDR5 support is up to 2133 megabits per second. Why is DDR5 support lower than DDR4? Good question. So if you look at the DDR5 JEDEC specification, it states that DDR5 support is between 2000 megabits per second and 2100 megabits per second, or above 3200 megabits per second. So for Avant, it falls within the first supported range, and that's why the cap is at 2133. Okay, I see one more question here. You mentioned the Avant IP has a provided example design. What does the design contain, and where can I find information on it? So you can find more information on the example design and what it encompasses in the IP user guide. But to answer your question, The example design consists of a training engine and a traffic generator, which are encompassed within a RISC-V processor, as well as a UART interface and GPIO connections to that you can hook up to LEDs. Okay, another one here. Does Lattice have a solution to address the situation where you want to connect multiple controllers to a single memory interface? So I'm not sure I fully understand the question, but I think what you're maybe asking is there a way to have multiple controllers that can control the actual LPDDR4 or DDR protocol that you're targeting? The answer is yes. We do have a multi-port memory controller that is being developed. So that will essentially allow you to have multiple AXI connections that will be able to interface with whatever protocol you select. Do you have any preliminary power measurements? So I'm assuming you're asking for Avant. If so, right now, what I can tell you is that for a 32-bit interface that's running at 1066 megahertz, we're seeing about 1.06 watts as the power measurement. Okay, so I see there's a lot more questions here. Unfortunately, we're out of time and I can't get to all of them, but we will follow up over email for any questions that were left unanswered. Thank you so much for attending this training session. I hope you found it useful and have a great day. Thank you.